Welcome to Math Science History. I'm Gabrielle Burchak, your host, and today we're going to do some deep, dark research into the history of understanding black holes and how it even got its name. By the time you are done listening to this podcast, you're going to know so much more about the study of these dark vacuums of nothingness. In the year 415, the infamous philosopher and mathematician Hypatia of Alexandria, Egypt, was savagely murdered by church monks. This murder shocked the Roman community and its government leaders. Hypatia was known far and wide as a respected philosopher, mathematician, government advisor, and a professor. Hypatia, The Sum of Her Life, is a book that I wrote that looks not just at the circumstances surrounding her death, but also at the sum of her entire life. I weave in the details of her education, disciples, Neoplatonic philosophies, female contemporaries, and the many mathematics that she wrote and taught about. There is truly more to Hypatia's life than her death. Hypatia, The Sum of Her Life, written by me, Gabrielle Burchak, is now on sale on Amazon. Buy your copy today. Imagine a place in the universe where time stops, where space folds into itself, and where not even light can escape. A place that devours everything, matter, radiation, even information. Now, imagine the scientists who tried to explain it and were laughed at, ignored, or dismissed as absurd. This is the story of black holes, perhaps the most mysterious and misunderstood objects in the cosmos. And believe it or not, the journey to understanding black holes is as strange and fascinating as the holes themselves. It is a story that spans centuries, from the Enlightenment era, stargazers to physicists in trench coats, from the elegant math to the cosmic PR disasters. And yes, even a moment when the term black hole was considered scandalous. The idea that gravity might be powerful enough to trap even light isn't new. In 1783, the English natural philosopher Reverend John Mitchell wrote a letter to Henry Cavendish proposing certain properties of a, quote, dark star. Using Newtonian physics, he reasoned that if an object were massive and compact enough, its gravitational pull could exceed the speed of light. Light, he argued, wouldn't be able to escape. This concept predated Albert Einstein's theory of black holes by over a century. A few years later, the French mathematician Pierre-Simon Laplace made a similar suggestion, noting that the escape velocity of such a body would exceed the speed of light. And for more information about Pierre-Simon Laplace, please be sure to check out my previous episode where I actually go back in time and interview him. Anyhow, these musings that he had were clever, but they lacked physical evidence and were based on classical mechanics, which assumed that light was made of particles. When the presentation of wave theory gained traction in the 19th century, the idea of dark stars fell out of favor and the notion faded into obscurity. In November 1915, Albert Einstein presented his general theory of relativity, a radical new model of gravity in which mass and energy bend the very fabric of space and time. Just a few months later, in 1916, Karl Schwarzschild, writing from the front lines of World War I, discovered the first exact solution to Einstein's field equations, revealing a peculiar critical radius, which is now known as the Schwarzschild radius, beyond which a star's gravity would become so intense that not even light could escape. Yet Einstein himself remained skeptical that nature would allow such extreme objects to exist. He reportedly remarked that nature abhors a singularity, doubting that the universe would permit mass to collapse into an infinite point of density. So, needless to say, there was a reluctant revolution. And up until this point, most scientists believed that the death of a star meant it collapsed into a white dwarf. So, enter the brilliant theoretical physicist Subrahmanyan Chandrasekhar an Indian-born scientist whose highly awarded career spanned the years at Cambridge, Harvard, University of Chicago, and Yerkes Observatory. At the age of 19, yes, just 19 years old, he began to determine the calculations within a white dwarf star and found that remnants within a star that are 1.4 times larger than our solar system's sun would be too large to create a white dwarf. This value that he determined is known as the Chandrasekhar limit. It was brilliant. However, at a 1935 meeting of the Royal Astronomical Society, physicist Sir Arthur Eddington publicly ridiculed Chandrasekhar, stating that, quote, there should be a law of nature to prevent a star from behaving in this absurd way, unquote. Eddington backed up his statement with an argument that perfectly reflected what Chandrasekhar was theorizing. In other words, he used Chandrasekhar's theories to argue against himself. Regardless, Chandrasekhar was embarrassed and actually considered quitting the field of physics. He was only 19 years old. And this one gets me because he was just a kid. So, heads up, tenured professors. Sometimes these young kids know what they are talking about. So, in 1939, physicists J. Robert Oppenheimer and Hartland Snyder published a groundbreaking paper that mathematically described how a massive star could undergo unstoppable gravitational collapse, forming what we would now recognize as a black hole. Their model, titled, quote, on continued gravitational contraction, unquote, predicted that beyond a certain point, no known force could halt a star's collapse into a singularity hidden behind an event horizon. Yet, at the time, almost no one paid attention. World War II erupted just months after their paper appeared, shifting the world's and the scientific community's attention toward wartime research like radar, nuclear fission, and weapons development. When physicists finally returned to pure theoretical work after the war, it would take decades before Oppenheimer and Snyder's startling insight was fully appreciated and folded into mainstream astrophysics. It was like Oppenheimer and Snyder discovered a monster in the basement, but everybody on the main level was fighting zombies and couldn't go into the basement to look. After Oppenheimer and Snyder published their 1939 paper, there was a silent period on the study of black holes. However, in the late 1940s and through the 1950s, a few important but quiet theoretical developments about gravitational collapse and extreme objects did happen before John Wheeler really made black holes a mainstream discussion in the 1960s. Almost immediately after Oppenheimer and Snyder published their paper, Einstein published a counterpaper titled On a Stationary System with Spherical Symmetry Consisting of Many Gravitating Masses. In this paper, he argued that true gravitational collapse wouldn't happen in nature. He believed that internal pressures inside matter would prevent a singularity from forming. And due to his long existing credibility, it added to mass skepticism over Oppenheimer and Snyder's work. In the 1950s, Italian mathematician Tullio Levi-Civita analyzed Einstein's field equations that were related to strong gravitational fields and the collapse of a star. Though he didn't fully address black holes, he laid a mathematical groundwork about extreme space-time behaviors. In the late 1950s, David Finkelstein published a paper titled Past-Future Asymmetry of the Gravitational Field, which described the event horizon as perfectly all part of space-time. He referred to it as a one-way membrane in which matter could fall inward but never escape. This one-way membrane directly refers to the Schwarzschild radius. Then, in the late 50s, physicist Werner Israel began to formalize an idea that once a collapsing star is formed, it remains simply mass, charge, and spin, stating that all the other details do not matter. Theoretical physicist Jacob Bekenstein later credited Israel's theory, stating that black holes have no hair, meaning that black holes are simply as Israel states. They have mass, charge, and spin, and any other matter that might fall into the black hole's event horizon is not visible. It eventually came to be known as the, quote, no-hair theorem. Eventually, John Wheeler ran with it. John Wheeler's influence went far beyond clever naming. In the late 1950s and 1960s, he played a crucial role in pushing the physics community to take the idea of a total stellar collapse seriously. Wheeler's work helped transform black holes from a mathematical curiosity into a cornerstone of modern astrophysics.
We'll be right back after a quick word from my advertisers.
At the heart of it all is the dramatic fate of massive stars. When a star much larger than our sun exhausts its nuclear fuel, it can no longer produce the internal pressure needed to counteract the relentless force of gravity. For moderately sized stars, collapse halts at the white dwarf stage, supported by electron degeneracy pressure. And for more information about electron degeneracy pressure, please be sure to listen to my next podcast on Flashcard Fridays this Friday on Subramanian Chandrasekhar. But back to black holes. For even heavier stars, neutrons resist collapse, creating neutron stars. But for the most massive stars, even these quantum pressures fail. There is no known force strong enough to resist gravity's pull. Collapse becomes unstoppable. As the star implodes, its core compresses further and further. Eventually, it reaches a critical threshold known as the Schwarzschild radius. As I noted before, the Schwarzschild radius marks the boundary beyond which escape is impossible, not just for matter, but even for light. This boundary is what we now call the event horizon, not to be confused with the Sam Neill cringe movie Event Horizon. It's really a cringe movie. It's best reserved for nights of drinks, weed, and cringe movie watching, and definitely popcorn. Lots of popcorn. But again, back to black holes. Sorry, I love to digress. Inside the event horizon, space-time itself is so warped that all paths, even those that would normally move outward, are dragged inward. The core of the collapsing star is theorized to continue shrinking, collapsing down to a single point of infinite density known as a singularity. At this singularity, the known laws of physics, particularly general relativity, break down. It's a region where quantities like density and curvature become infinite, and our current scientific models can no longer predict what happens. Wheeler's genius was not only in recognizing this grim endpoint, but also in framing it in a way that physicists could grapple with. In particular, he emphasized that black holes were not merely exotic anomalies. Rather, they were a natural consequence of Einstein's equations, demanding exploration, not dismissal. Wheeler's analysis also helped introduce a new way of thinking about black holes. Instead of being pathological, they could be simple and elegant. Working with physicists like Kip Thorne and others, Wheeler added to the no-hair theorem, stating that everything else about the collapsing star, its complex internal structure, its chemical makeup, its quirks, are lost forever beyond the event horizon. This idea that black holes are simple objects despite their violent birth helped scientists not only accept their existence, but also to model them mathematically and explore their behavior through thought experiments and eventually observational evidence. Wheeler's advocacy came at the perfect time. Through the 1960s, technological advances like radio astronomy and X-ray telescopes were uncovering phenomena that fit beautifully with black hole models, mysterious, powerful sources of radiation with no visible counterpart, like Cygnus X1. Meanwhile, theoretical work by Stephen Hawking, Roger Penrose, and others were making it increasingly clear that singularities were not rare freaks of nature, but inevitable outcomes under many conditions in general relativity. In this way, Wheeler's efforts closed the gap between theory and observation by championing black holes not just as possibilities, but as predictable, observable objects. Wheeler changed the scientific landscape forever. His contributions reframed black holes from speculative oddities into crucial testing grounds for understanding gravity, space-time, and quantum theory. Today, thanks in part to Wheeler's work, black holes are no longer cosmic mysteries hiding in mathematical margins. They are essential pieces of the universe's story, labs where the boundaries of physics are pushed to their breaking point. The now familiar name black hole was not always part of the scientific lexicon. Wheeler is widely credited with popularizing the term between 1967 to 1968. But it had surfaced a few years earlier in more informal contexts. In fact, the phrase appeared in print as early as January 1964. Science newsletter reporter Anne Ewing wrote that if enough mass were added to a dense star, quote, such a star then forms a black hole in the universe, unquote, describing findings at a 1963 American Association for the Advancement of Science meeting. This was the first published use of black hole in the astronomical sense, beating a Life magazine story by Albert Rosenfeld 1 week later. Neither Ewing nor Rosenfeld identified who actually coined the phrase at those meetings. It was likely tossed around informally by scientists chatting over drinks, or, as I like to call it, drinking and deriving. Historian Marcia Bartusiak later traced the root of the term to Princeton physicist Robert H. Dick, who around 1960 had jokingly likened a completely gravitational collapse to the Black Hole of Calcutta, which was a notorious prison from which no one escaped. This morbid quip, suggesting an object one can enter but never leave, apparently evolved into the pithier label black hole that began circulating at conferences in the early 1960s. For a few years, black hole remained a casual, even controversial term. Many physicists still used more technical descriptions like completely collapsed object or frozen star. And the concept of such an object was itself viewed with skepticism by some. Wheeler, as well as Roger Penrose, initially were no exceptions. Wheeler had doubts about truly collapsed stars, but by the late 1960s, he had come around to Oppenheimer's 1939 prediction of collapse to a singularity. In December 1967, during a lecture in New York, Wheeler found himself repeatedly saying the cumbersome phrase, gravitationally completely collapsed object. As he later recalled, someone in the audience interrupted and suggested, why not just call it a black hole? Wheeler immediately recognized the value of the name and said it was perfectly appropriate for such an object, as he put it. Just a few weeks later, on December 29, 1967, Wheeler boldly used black hole in an address to the American Association for the Advancement of Science annual meeting in New York. He even included the term in the published write-up of that talk, titled Our Universe, the Known and Unknown. It was in the spring 1968 edition of American Scientist, marking the term's formal entry into scientific literature. By attaching his considerable prestige to the new, catchy name, Wheeler effectively gave his authority to the term, as one historical analysis notes. Physicist Kip Thorne later quipped that Wheeler became the, quote, enthusiastic baptizer of black holes after overcoming his own earlier doubts. From 1968 onward, use of the term exploded both in academia and in popular culture, firmly replacing the clunkier alternatives.
We'll be right back after a quick word from my advertisers.
When Wheeler began using black hole publicly, the scientific community's reaction was mixed intrigue and mild discomfort. Many younger astronomers and physicists embraced the term for its brevity and vivid imagery. It, quote, immediately captured the imagination of scientists, unquote, according to some historians. However, some establishment figures and editors were initially wary of its informal, almost irreverent tone. Wheeler himself noted the advertising value of the name. It was attention-grabbing, but that quality also made it sound almost too colloquial for formal discourse. In fact, science writer Marcia Bartusiak observed that what Wheeler really provided was permission. He never claimed to have invented black hole, but his use of it legitimized the term in scientific circles. Bartusiak writes that he had the authority to give the scientific community permission to use the term black hole. She implied that without Wheeler's blessing, others might have hesitated to adopt such a punchy phrase. Indeed, before 1967, researchers often kept black hole in quotes or opted for technical jargon. Even Soviet physicists preferred terms like frozen star in the early 60s. And in France, the literal translation, trou noir, raised eyebrows. For a time, French scientists used the more genteel astre oculus, which meant occluded star, instead, until trou noir eventually won out. These hesitations show that the term was initially seen as slang, evocative and handy, but not yet wholly respectable. Yet any serious pushback against black hole quickly faded as evidence for these objects mounted at the end of the 1960s. Once Cambridge astronomers announced the first pulsars and candidates for black holes in 1967, the community needed a convenient name, and Wheeler's choice fit the bill. By 1970, research papers freely used black hole without apology, and the term was appearing in journal titles and conference proceedings. In short, what began as an informal quip became an ideal name for the phenomenon: succinct, descriptive, and memorable. Any initial unease was outweighed by the term's explanatory power. As one Physics Today article put it in 1971, the name black hole conveys in 2 words the chief properties of these objects: a hole in space-time that is black because not even light escapes. Although black hole is commonplace now, it provoked some amused reactions and some off-color jokes in its early years. And really, who could refrain from making off-color jokes? I couldn't. The term's stark literalness and possible double entendres did not go unnoticed. At the 1967 lecture where Wheeler first adopted it, the audience reportedly chuckled at the suggestion. Then, when Wheeler added that black holes have no hair to describe how these objects lack distinguishing features, it, quote, prompted some controversy and generated a series of problems with the editor of the Physical Review, who found the phrasing too flippant for a series journal. This incident hints that even black hole initially struck some as too irreverent. In hindsight, black hole was the perfect name for one of the most radical predictions of modern physics. Its journey into acceptance was not instantaneous. Early on, it was mocked by some as jargon from the hotel bar circuit of astronomers and even deemed unseemly in certain languages. What started as a conversational nickname, even a bit of a joke, is now an indispensable concept in astrophysics. The initial chuckles and critiques have long been overshadowed by the term's utility and popularity. It was even useful during Stephen Hawking's theories, as he stated that black holes, quote, ain't so black. In the 1970s, black holes transformed from theoretical oddities into dynamic players in the universe, thanks in large part to Stephen Hawking. In 1974, Hawking stunned the scientific community when he did propose that black holes aren't so black. Instead, black holes emit tiny amounts of radiation, now famously known as Hawking radiation. This groundbreaking idea suggested that black holes could eventually evaporate and disappear, challenging the notion that nothing could ever escape from them. Around the same time, astronomers made another monumental leap when they identified Cygnus X1, a strong X-ray source in our galaxy. Observations revealed that Cygnus X1 was a binary system with one visible star and an unseen companion so massive and compact that the only plausible explanation was a black hole, the first real observational evidence of such an object. Decades later, in 2015, black holes again dominated headlines when the Laser Interferometer Gravitational Wave Observatory detected gravitational waves for the first time. The ripples in space-time caused 2 black holes merging more than 1 billion light years away. I will never forget that. It was a stunning confirmation of Einstein's century-old predictions and a thrilling new way to observe the cosmos. Once, black holes were nothing more than rejected mathematics, strange predictions scribbled in the margins of Einstein's equations, too wild, too impossible for nature to allow. They were the monsters science dared not believe in, haunting the theoretical shadows where few physicists wanted to look. But over time, these shadows sharpened into reality. Though relentless questioning, brilliant insight, and a willingness to follow the math wherever it led, black holes moved from theory into confirmation, from skepticism to the front page of human discovery. Today, we know they are real. We have seen the fingerprints of their existence in the X-rays of Cygnus X1, heard their cosmic mergers through LIGO's detectors, and glimpsed their ghostly silhouettes through the Event Horizon Telescope. Black holes, once banished ideas, now anchor our understanding of space, time, and the limits of existence itself. And in their journey, from rejection to revelation, they tell a story that mirrors our own. We, too, live in a universe that challenges what we believe is possible. We, too, wrestle with invisible forces, with mysteries we cannot yet name. Black holes remind us that truth does not vanish simply because it seems too strange. It waits for us to be brave enough to see it. In the end, the story of black holes is not just the story of collapsing stars. It's the story of human curiosity, how we confront the darkness, how we fall inward, how we rise again with new understanding. Somewhere in every black hole's silent pull is the echo of our own search for meaning in the cosmos. Thank you for listening to Math, Science, History. And until next time, Carpe Diem.
Thank you for tuning in to Math, Science, History. If you enjoyed today's episode, please leave a quick rating and review. They really help the podcast. You can find our transcripts at mathsciencehistory.com. And while you're there, remember to click on that coffee button because every dollar you donate supports a portion of our production costs and keeps our educational website free. Again, thank you for tuning in. And until next time, Carpe Diem.